Hello everybody. In today's video, we are going to solve another problem from LeetCode's top interview 150 problem list live. So far, we have solved all the problems till jump game 2. If you haven't checked out my videos where I solve those problems, please go to my channel and check them out. The next one is h-index. So let's read the problem and make sure we understand what this is. Given an array of integers, citations, where citations of I is the number of citations a researcher received for their ith paper, return the researcher's h-index. According to the definition of h-index on Wikipedia, the h-index is defined as the maximum value of h such that the given researcher has published at least H papers that have been cited at least H times. Wait, okay, I need to read that again. Maybe let me read it very slowly. The H index is defined as the maximum value of H such that the given researcher has published at least H papers that have been cited at least H times. I see, I see. I think so. Okay, so first the array given to us is citation count for specific papers for a given researcher, right? So this means first paper was cited 3 times, second paper was cited 0 times, third was cited 6 times, fourth was cited 1 time, and fifth was cited 5 times, right? And given such an array, which is citation count for a bunch of papers, we need to figure out the H index. And I think the H index is the maximum number of papers for which there are at least that many citations. I think that is kind of how I would have put it. At least that is makes it clear to me if I put it that way. So for example, in this case, it is 3 because in this case, there are 3 papers, the first one, the third one, and the fifth one, which are cited at least 3 times, right? And the at least part is what makes the problem very interesting. Okay, now, yeah, we just talked about that. Let's figure out how to do this. I mean, one approach that I immediately thought about is that, well, actually, it's not still a full approach that I have thought about, but I mean, one thought is that the maximum possible value for H index is actually the length of the array because this is the number of papers, right? There are 5 papers this researcher has published. So if the H index is, hey, the number of papers which are published at least that many times, and then it is the minimum of basically the number of papers and the citation count for those papers, then in that case, it cannot have, the H index cannot be more than 5, right? So yeah, I think that is a thought, not a solution yet. But I mean, yes, actually, yeah, okay, I see. I think I know why I thought I had a solution. I think that can be converted to a solution, right? So, for example, if the maximum H index is 5, we could first try that, right? And see if there are 5 papers that have been cited 5 times at least, right? Then linear scan it, right? So the first question, for example, in this case, we ask is 5 H index? Is H index equal to 5? Is H index equal to 5, right? And the answer is given by basically scan the array and count how many papers are cited at least 5 times, right? And if that is bigger or equal to 5, then yes, 5 is the best H index and we can return. If not, the next question is H index equal to 4, right? And then we can do the same thing. Hey, scan the array to see how many papers are, and count how many papers are cited at least 4 times and so on. So I think that is, yeah, that is an approach that would work. Now, it doesn't feel like it's the most efficient approach because it's like, O of n square, but I think it's still worth implementing it. Maybe it will give us some insight into a better approach. Okay, so I'm going to implement this in a helper because, if we end up coming up with some better approach, we can implement it in a different one. H index by counting, I don't know, there's some name there, citations. Okay, oh, sorry, citations. Yep, that's correct spelling. Okay, so like I said, let's start the potential H index from the maximum possible value. So for int H index equal to, and maximum possible value is dot length. Is it dot length or dot length minus 1? No, it's actually dot length because it's the number of papers, right? The maximum number of papers is what is the maximum possible H value. And the number of papers will be given by the length, not length minus 1. Okay. And then H index is greater or equal to 0 because that's the minimum value of H index plus, minus H index because we are going from bigger to smaller values. Okay. And here inside we basically count how many papers have been cited at least that many times, right? So let's say count equal to 0, and then we say I equal to 0, I is less than citations dot length plus I. And okay, so here we go slow. Wait 1 second. So citations of I has to be, yeah, that has to be bigger or equal to H index. And if that is the case, we do plus count, right? Yep. And then we say if count is greater or equal to, wait a minute. So, okay, so yeah, if count is greater or equal to H index, then we return H index, right? There you go. I think that should work. Yep. Okay. And well, outside we need to return something. I think we return 0 because I mean, although the last 0 here, the last iteration of the loop would have returned, but Java would complain if you are not returning in all code paths, so we have to return here. So let's return 0 there. Okay, let's see if this works. It's a very interesting problem actually. Return this and citations, right? Okay, there you go. Okay, let's run this. Accepted. Okay, that's good. Although I do want to add a couple of more test cases here. So for example, what I was thinking is that what if all of them is phi, then it should return phi, right, as the H index. And in fact, not only that, if in fact there were phi numbers bigger than phi, but there are only 5 papers, it should still return phi, 97 and 96, right? So let's see if that works. Okay, so that worked as well. Okay, got it. Now, actually, while I was writing this, I just realized one thing, right? And I don't know if I still have a full approach from that thought, which is more efficient, but thinking aloud again, live solving the problem is fun because of that. Okay, so thinking aloud, actually here what we did is we had to linearly scan to figure out how many values are bigger than a specific number, right, or equal to a specific number. For example, how many papers have more than 3 citations, then we have to linearly scan 3 0 6 1 5 and count. But what if we sorted, right? So and sorted in descending order. So if we say 6 5 3 1 0, then what will happen is we kind of don't we get rid of that inside for loop to linearly count, because if you think about it, if we are at this point, then all the papers before that, the citation counts before that, are going to be bigger, which means we have that many papers which have, which have 3 citations or more. So actually, let me write this down, right? So 1 2 3 4 5. So what I mean is, here the paper count so far is 1, right? It's the first paper, right? Here 6 citations. Now we have already seen 2 papers, right? Now we have seen 3 papers and 4 papers and 5. So the paper count increases, citation count decreases because we sorted that in the decreasing order. And so what we are actually trying to find, if we sort it this way, is, okay, so here, for example, the H index is just 1 after we read the first number 6, because we only have seen one paper. Although it has 6 citations, the paper count is 1. But we could keep going because we could see more, because the citation count is still bigger than the number of papers. So there could be a better H index, right? So we keep going. We look at 2 and we say, okay, 5. Okay, now the H index is 2 because there are 2 papers and they have at least 5 citations. So the H index is 2. So we improved our H index. And now we go to 3 and we do the same thing. We improved our H index. But at this point we can stop, because now we got paper is more, but then citations are lower. There's only one citation. So yeah, so I think what we are trying to find is, where do they cross, right? The paper count is increasing, the citation count is decreasing. Where do they cross? And that is the point, which is our H index. So if we sort, we can do that linearly, sort in descending order. Okay, so that would be an improvement over this, because this implementation is O of n square. It's 2 nested loops which go O of n times, while in this case we would be sorting, which will be O of n log n, but then we'll be doing another O of n work, but that will still make the algorithm O of n log n overall. So I think I'm going to try to implement that. So let's say compute H index by sorting. Okay. Mint citations. Now sorting this, yeah, the Java, this is a very annoying thing in Java, unless they have fixed it in the later versions. But if I remember correctly from back in the day when I was very actively coding in Java, Java does not have an easy way to sort basic data, arrays of basic data types in descending order. So we can do arrays.sort, and that will sort an array of basic data type like integer array, fine, but there is no comma descending or something like that, right? Type descending or anything like that. And there are ways to sort descending arrays if they were arrays of objects like integer, but I don't want to convert, like, all integers in an array to that many integer objects, because that many objects then have to be collected by garbage collector when we are done, and that's not a good idea. So anyway, I think so what we gotta do is we have to sort, and then we have to reverse the whole array. I honestly do not know or remember if there is a ready-made helper in Java library to do reversing, but I'm just gonna quickly write that. Reverse array int a. Sorry about that. Okay. Yeah, so the way we reverse is we do a dot length minus 1. So we start left on the 0th index, right on the last index, and we keep on swapping elements until left is less than right. And I don't want to forget this, so I generally do this a lot. I first do that and then write the code above that. Okay, in while loops especially, for loops are okay. Okay, now we swap. So we do end temp equal to a of left equals a of right, and a of right equals temp. There you go. Okay, so that's our reverse array helper. Let's call that here. Citations after sorting we reverse, so now it should be sorted in descending order. Okay, and now let's try to implement this approach. I'll take that there. Okay, so what we have is we already have 65310, and what we gotta do is we have to say int h index initially 0, and remember we are going to increment h index as we go, but stop where the number of citations becomes lower than the index value. Okay, so for int I equal to 0, I is less than citations dot length plus plus I. Okay, and then citations of I gives us the number of citations. So let's go slow here. Citations of I is the number of citations, and if that is greater or equal to, now we got to do I plus 1 because the number of papers is given by I plus 1. I could directly write that there, but let me just do paper count and just do I plus 1. It just is a little bit easier for me to confidently understand the code. Is greater or equal to paper count, then we just do h index there, right? And yeah, I think, do we break under any condition out of the loop is what I'm thinking about. Yes, so we could also break out, right? So we could say else, yeah, 1 second. Actually, yeah, we can do this, right? We can say if citations of I is less than paper count, then we just break, right? And otherwise we just increment h index. Yeah, this should work because short circuiting is actually good for cases where we don't need to look forward. It's the same thing, I just reversed it, but because we could break in else, I just did it this way. Okay, and in fact we could actually probably even add this as and here, but I'm going to keep it this way because it's just a little bit easier to understand. Okay, I think then we just return h index here, right? So yeah, this is just finding that boundary we talked about. That the number of citations is decreasing, the index in the array is increasing, or paper count is increasing. We're trying to find that intersection. Okay, so let's see if this works. This I'm nervous about. The other approach was a little bit more straightforward. Oh, cool. So it did get accepted. Okay, that's good. In fact, one thing I was thinking about when I wrote this is that you guys probably know this, but whenever the user gives us an array like this, like actually this is the function that is public, so hence called by the user, changing that array by sorting it is actually not a good idea. It's in most cases, right? In some rare cases, it might be okay, but the user doesn't expect us to reshuffle their array for an operation like calculate h index, right? They might be using this citations array elsewhere, and that order of paper count might actually, or citation count might actually matter to them, right? So in this case, I mean, there's nothing like that given to us that we have to worry about, but in reality, I wouldn't do that. And so in reality, actually, we should make a copy of this input citations array and then sort that and stuff like that. So even though this implementation is O of 1 memory, like if we do the right thing for the user, it will be O of n memory. Just a note that came to my head, so I wanted to share that. Okay, maybe we'll try to submit this and see, like how are we doing on time compared to all other submissions which are successful. And also runs more test cases, so that's always good. Okay, so we did get accepted. Our time beat about 68% submissions. Okay, that's interesting. That's not super high. And okay, memory beat 96.33. Okay, that's interesting because that kind of tells me maybe there is a better approach. Now, one thing I did think about, and I do not think that will help improve the time, especially like anything meaningfully, is that instead of running a loop like this, we could actually do a binary search. And the reason is because, it's sorted, right? We have these citation counts decreasing, we have the paper count increasing. So we can do the binary search and go to the middle, see, whether that's where the citation count has actually crossed the paper count or not. And if not, then we go on one side. And if yes, then we go on the other side, right? But the reason I think it will not really improve much in time is because the time is dominated by sorting, right? This is n log n, this is O of n times log n, and this is also n O of n reversing. And so relative to that, removing this O of n time and making that O of log n is not going to really make a major difference. So that tells me that maybe there is a linear approach because this dominates the complexity, right? Okay, so let's think about that a little bit. Let's go back to this example. I mean, basically we can't sort, right? So somehow can we do this without sorting? Okay, let's see. So one thing is, if we have to do this without sorting, can we do the following? Just trying to think aloud here. So let's say that we scan through this array and yeah, I think, okay, so this might lead to something useful. Okay, so remember the maximum number of citations, if it like in this case it's 6, right? The maximum citations is 6. That being more than number of papers doesn't really matter because this could have easily been 5, right? And that would still give us the right answer because the number of papers is 5. So having citation, if this was even 100, it wouldn't really matter, right? So because there are only 5 papers, so your H index couldn't be more than 5. So anyway, so that's one thing. And the second thing is that means what if we allocate an array where array of size n plus 1, where n is the number of, papers here. So it's kind of various h values. Think of it that way, right? The arrays of various h values, but don't think of it as h values. Let's think of it as the papers. So there are 5 papers. Actually, no, these are citation counts actually. So they are potential H values. Okay. So let's say we allocate an array of size 6. So they have 0, 1, 2, 3, 4, 5, and those are all the citation count, right? And we are taking the citation counts and converting them to paper count. So here, remember, the indices means the papers, right? 1, 2, 3, 4, and 5, right? And each of those papers actually have citation count. Here, the indices, I mean, this could start at 0 actually. So 0, 1, 2, 3, 4. Here the indices means citation count. So how many, and the values are the paper count, right? So hey, how many papers have 0 citations? How many papers have 1 citation? How many papers have 2 citations? How many have 3 citations, 4 and 5, right? And if we fill up an array like that, so let's fill it up actually. How many citations, at least visually, let's fill it up first, right? How many papers have exactly 0 citations? 1 paper, right? How many papers have exactly 1 citation? 1 paper. How many papers have exactly 2 citations? 0 papers. 3 citations, 1. 4 is 0 and 5 is actually 2. And the reason 5 is 2 is we can't record 6 if we are only allocating an array of size 0 to 5, right? Citations, and that is okay because our h value can never be more than 5 anyway. So consider 6 to be logically 5, so we make that 2, right? And basically there are 2 papers with 5 citations. Okay, if we fill up this array like that, and let me actually do the array symbol here so we can distinguish between indices and array, then we can actually go from behind to this side and see where we are finding our best H value. For example, here we say, okay, how many papers are there with 5 citations? Only 2. Well, that cannot be our H index, right? It has to be 5 or more. Okay, so we keep going. But these 2 contribute towards 4 as well, remember, because there were 2 papers that were cited 5 times. That can be contribute their 2 papers towards a potential H value of 4. So we keep summing up those values, right? But 2 plus 0 is still 2. So there are still only 2 papers which have 4 or more citations. But now we have 3 papers with 3 or more citations, right? And that's our H value, and we stop there because we are not going to find a better H value going here because now, yes, we have 3 papers which have 2 or more citations, but 3 was better than 2, right? So that I think gives us the linear approach. And and the thing is, allocating an array, sure, we are using of and memory extra. But if you think about it, in the other case, like I said, we cannot really rearrange the array of the user where we are just doing an operation like computing h index, right? So here also, if we wanted to do the right thing, we would copy the citations array and make another array and sort that. And so it's actually not a big deal. So it's not even a trade-off compared to this approach in my mind, if we wanted to do the right thing in the other approach. Okay, so let's try to implement that. Let's just call this compute h index citations. Okay, so what are we doing first? We are allocating an array which is paper counts, not citation counts. And we are going to have one more element into that, because remember the citations dot length plus one, right? Because citations can be 0 as well, right? And the maximum number of citations can be more than the length of the array, but we will bound it to the length of the array because h index cannot go beyond that. Okay, so we are doing that. Now we have to fill that. Now Java already initializes all of those values to 0. So yeah, so we should be good there. I equal to 0, I is less than citations dot length plus I. Okay, there you go. Now remember, with the value of citations of I, so let's actually say int citation count equals citations of I, right? And if that is bigger than the length of the array, we want to make it to equal to the length of the array, right? So if citation count is greater than citations dot length, then we just say citation count is equal to citations dot length, right? That's the number of citations. Okay, now the exact number of citations for a specific paper is here. So now what we need to do is we need to increment the number of papers with that many citations, right? So we go to the paper counts array, add the citation count index and plus that, right? Actually my convention is to do plus before. You could do the other way, it doesn't matter, right? So plus paper counts of citations count, right? Okay, I think that sets up our array very nicely. Again, what we are doing is we are taking this array and just to go through this a little bit. So when we look at 3, we go to index 3, 0, 1, 2, 3, and we increment that by 1. It was 0 initially, right? And then when we look at 0, we increment index 0 by 1. When we look at 6, so we convert 6 to 5, and then we increment that by 1. So this would have become 1, and so on and so forth, right? So this whole array is now constructed after this for loop. Now that that is done, we basically go in the reverse order like we said. So we go from int I equals paper counts dot length minus 1, I is greater or equal to 0 minus I, right? And oh, so we do need to keep a running count of papers. So total count equal to 0, total papers, and we say total count plus equals paper counts of I, right? We add that many papers to the running count. We say, okay, if now our total count, so we have total number of papers. If the total count is, that is greater than or equal to the index I, then we return I. And here we return 0, right? So that's what we are doing here, right? We were going here and we say, okay, total count is 0 plus 2, index is 5. But if index is 5, meaning how many papers have 5 citations? Well, there are only 2 papers. That's not our h index, right? But as soon as our count becomes bigger or equal to the index I, then that is our h index. So there you go. I think this should work. The compute h index is the only name. Let's run that. Okay, compiler, that should be okay. Oh, int, okay, 1 second. That should be easy to fix. Int, are there more errors? Citation count. Yeah, I need to do citation count, not citations count. There you go. Oh, cool. It is accepted. Very nice. Okay. Let's submit this and see what our performance is this time. Oh, okay, cool. That is amazing. I did not expect to beat everybody, but looks like our submission beats all other submissions in terms of memory. And it beats only 10.61% in in time it beats 100% and only 10.61% in memory. Yeah, we are using extra memory. Like I said, if we try to do the right thing in another approach, it has to also use extra memory. So there you go. Again, just to very quickly summarize, this is O of n time complexity and O of n memory complexity, right? Very straightforward, but just for completeness. Cool. Hopefully that was very helpful. This was a very interesting problem. I had fun doing it. Uh, and yeah, if you're liking what I'm doing on this channel, please feel free to subscribe to my channel. I'll really appreciate it. And hit the thumbs up button on the video. See you guys next time.